Alrighty, so welcome to chapter 13. Right now we are going to do the 13, 14, 15 chunk. And since the 12, 16, 17, 18 chunk is the most recent one we've been working on, we will do that last. So first we're going to talk about conjugation. So as we know, conjugation is when we have two double bonds separated by a single bond. So this is conjugated. When we have two double bonds that are separated by more than one single bond, we call this isolated. And when we have two double bonds on the same carbon, we're going to call that cumulated. And when we talk about stability, conjugated is really stable. So I'm going to say V stable. Cumulated is V unstable. And isolated is in the middle. So we can say this is the most stable, followed by isolated, and cumulated is the least stable. We're going to put a pin in that for now. Real quick, okay, cool, that was my charger. Real quick, we're going to talk about configuration versus conformation. And if we remember, configuration is when we have two single bonds with a double bond in the middle. And conformation is when we have a single bond in the middle of two double bonds. So, what we need to know is that for configuration, we're going to use EZ or cis-trans. Naming. We know that this guy, right here, is on opposite sides. And what I mean by that is the primary group is opposite to one another. So we're going to call this E. And then this one, that group, the two most important / biggest groups, are on the same side. So we're going to call that Z. And we know that E is more stable. For conformation, we're going to use S-cis and S-trans naming. This guy is S-trans because the groups are pointing to the opposite sides. And this guy is S-cis because they are pointing to the same side. And in this case, S-trans is more stable. The last thing is conformation. You can rotate. Configuration, you cannot rotate. So this one's locked in place. This one you can flip back and forth. All right. So, UV spectroscopy, there's a lot of stuff that goes into this, so I definitely recommend going back through SI and handouts and stuff to look at all the UV spec stuff. But the biggest thing I want to mention right now is make sure you understand the trend, right? So the more conjugation, oopsie. The lower the energy, because it's more stable, right? And so we can also think of this in terms of energy, wavelength and frequency. So energy and frequency are directly proportional, energy and wavelength are indirectly proportional. So low energy equals low frequency, which equals higher/longer wavelength. So if you remember this much, you should be good with the UV spec questions. Something that goes with UV spec is molecular orbital theory. Molecular orbital theory can be an hour review on its own, so pretty please check out the molecular orbital theory video and handout. And so that will be a lot more useful than just blurting through it really quick now. Okay. So we have our 1,2,1,4 addition reactions. We've done this exact reaction before. The reason for that is Dr. West loves this reaction, and I don't feel like making up a bunch of different ones. So let's review it one last time. We have our diene, and that is going to steal a hydrogen, give those electrons to the bromine. So the nucleophile here is going to be the double bond, and it attacks the hydrogen. And the electrophile is HBr. So when we do this, we attach our hydrogen here, and we get a carbocation. That carbocation can either just have the Br attached directly, or we can do resonance and have the Br attach all the way over here. So if Br just attaches directly to the carbocation, we have the 1,2 product. If we do resonance, we have the 1,4 product. So the nucleophile is A, the electrophile is B, the 1,2 product is C, and the 1,4 product is D. If we run down here for a moment, we have this kinetic versus thermodynamic table. And so real quick, let's fill it out. The kinetic product is going to be the one with the lowest activation energy. And the thermodynamic product is the one with the lowest, wow, that's what I meant, potential energy. So the kinetic product is the one that is formed in the least number of steps, aka less energy. Whereas the thermodynamic product is the one that has the most stable product. So if we scroll back up here, this guy was made in the least number of steps. This was made the fastest. It used the least energy. This one went through that extra step, used all that extra energy here, but it made a more stable double bond. So this double bond is di-substituted. This one is tri-substituted. So this has the most stable product. Therefore, it is thermo. This one was made in the least number of steps. So that one is kinetic. So thermodynamic product was D. Kinetic product was C. Sorry about that. My dad was like blasting the TV and I was like, I'm working, Dad. Okay. So, ta-da. This is 1,2,1,4 addition reactions. And we have our lovely kinetic thermodynamic product information. So let's go ahead and look at this, right? So this guy is going to be the starting material. And these two are the different pathways. I know that's a little bit different than the reaction diagrams you're used to seeing. But you know, just stick with me on this one. So these bumps up here are the activation energy. And these lines down here are the potential energy. So we have to find the lowest activation energy and the lowest potential energy. So the lowest activation energy is this one. And the lowest potential energy is this one. So in this example, A is both the thermo and the kinetic product. Ta-da! We zoomed past another chapter. Woo, we got this. Actually, I lied. We still have Diels-Alder reaction. I'm just going to talk about the bare minimum for the Diels-Alder reaction, because again, this could take an hour by itself. So please go and review Diels-Alder. But the most basic part of Diels-Alder is we have a diene and we have a dienophile. And those guys are going to react with one another. So, first of all, I like to number these. And we know that side 1 always attacks A. Side 4 always attacks B. And now we just go in a circle. And we get a cyclohexane. Ta-da! And so what we really need to talk about today is what a diene is, what a dienophile is, and what all this stuff means. So a diene is a conjugated diene, aka something that looks like this. And I'll zoom in while I write it because I'm writing kind of tiny. The diene is the nucleophile. The diene must be so it must be an S-cis conformation. And it likes electron donating groups because electron donating groups give electrons, which make better nucleophiles. On the other hand, dienophiles are any alkene or alkyne. They are the electrophile. And they don't have to have any specific configuration, but they are going to maintain configuration. So if we start cis, we end cis. If we start trans, we end trans. And they're going to like electron withdrawing groups because they steal electron density and make it more electrophilic. So let's zoom right out. And, you know, taking out all the actual reaction mechanism stuff, which I want you guys to go back and rewatch and review, this is all it boils down to. Knowing what the diene is, what the dienophile is, and how these guys react with one another. And something I did want to review is retrosynthesis, because we didn't get to spend too much time on that last time, and I know some people were confused. So, in a retrosynthesis reaction, they give you the product, and you have to find the starting materials. So I have a couple different ways of doing this. So I'm going to actually duplicate this, because I don't want to draw on the same thing 100 times. So, the first thing I always do is I look at these substituents, right? And I see a electron withdrawing group. And I see electron donating groups. And I know the electron donating groups want to be on the diene. The electron withdrawing groups want to be on the dienophile. So I know this area is the dienophile. I know this area is the diene. I also know that the double bond that we get in our final product, if I scroll up here, is going to be between carbon 2 and carbon 3, right? Because it moved from here to here. So, I can assume that this is carbon 2 and this is carbon 3. Which means this was carbon 1, that was carbon 4. And the first way I'm going to show you is doing the arrows backwards. So, I know that this is carbon 2, this is carbon 3. And this is the double bond I'm left with. So I'm going to just, in a different color, bring it back here. So I know that that double bond started between carbon 3 and 4. We broke this bond. And the electrons from here went to this bond. And so we can also fill in that this is carbon A and carbon B, which would mean this one broke. So these electrons went over here. And so we got, oh my gosh, excuse me, I'm so sorry. I'm so sleepy today. So we started out with this. And this. The other way to do it is a little bit less like nice, pretty, and exact. We are going to say, again, this is a withdrawing group. This is a donating group. And we can also say that this is carbon 2 and carbon 3. Right? We already talked about that. So we can fill in 1 for A and B. And so what you can essentially do is you can look at this and say, okay, my diene had to be something in general like this. And it had to be 1, 2, 3, 4. So all you have to do is fill in what's missing. So we have 1 and 1. Bam. Our dienophile looks like this. And it has a double bond here because we know if we break those two bonds, this has to be left with a double bond. Okay, so someone asked, is the diene always going to look the same? It's not going to look exactly the same, but it is going to have the same general structure to it. So it could look like this. It could look like that. It could look like this, you know, but it's always going to have the same general shape to it. Okay. So that's pretty much all I have for the retrosynthesis. And so we have finished chapter 13. Yay! For chapter 14, I am actually going to pull something up for you, so give me one moment. Alright, so I do have the exam 2 cheat sheet here because I am frankly too lazy to rewrite and redraw all of this, and it would be wasting a lot of time. So instead, I'm going to show it to you and we're going to talk about it. So in order to be aromatic, something has to be cyclic, planar, fully conjugated, and has to have 4n plus 2 pi electrons. To be anti-aromatic, it has to be cyclic, planar, fully conjugated, 4n pi electrons. To be non-aromatic, it has to break any of those 4 rules. And if you want to hear me explain all those things in extreme detail, please watch the SI session for this. That would be very helpful. I mostly want to focus on these little rules, right? Because they tend to be really confusing. So when we're talking about heteroatoms, we can either make them sp2 or sp3 hybridized. It really depends on the stability. The only heteroatom that cannot change between sp2 and sp3 is boron. And that is written here. So boron always has to be sp2 hybridized, which means that it can never donate any electrons because it doesn't have any electrons to donate. So, yes, okay. So whenever something is sp2, it's going to donate 2 single electrons, aka 1 pair of electrons. That's the max. So oxygen cannot donate 2 pairs, it can only donate 1. So if he draws both pairs out for you, that's just to trick you. If something is double bonded, so if that heteroatom is double bonded, it has to be sp2. You don't have a choice. Double bond always means sp2. And if it's double bonded, it only donates 1 single electron. Now, if it's double bonded outside the ring, it's basically, we're going to pretend it's a carbocation. We can pretend this whole thing doesn't exist because it's sp2 hybridized, and it donates 0 electrons. These are a lot of rules, so we're going to talk about a couple examples. I gave you guys all these answers because I know aromaticity can be kind of difficult at first, and I want you to do a lot of practice. But the ones I do want to focus on are this guy. So if the heteroatom, like I said, is double bonded, it has to be sp2, and it has to donate 1 electron, even if that means it's anti-aromatic. We don't have a choice. But if that guy was single bonded, like this example, it could choose to be either sp2 or sp3. So how do we decide which one it is? So we decide that by looking at, sorry, I looked at the time and I got distracted. We can look at the number of electrons that are in this ring. So if it's sp2, we get 4 pi electrons because we donate this, and we get anti-aromatic. If it's sp3, it's always going to be non-aromatic because it breaks the conjugation rule. So, aromatic is the most stable. It's super, super, super stable. Non-aromatic is bleh. It's in the middle. Anti-aromatic is really, really, really bad. So we always want to choose the most stable. In this case, we choose sp3, and we are non-aromatic because it is more stable. However, if we have something like this, sorry for all the moving around. So now we have a little bit bigger of a ring, right? And if we choose to be sp2, we end up with 6 pi electrons, which would be aromatic. sp3 is always non-aromatic. And so in this case, nitrogen will choose to be sp2 so that it could be aromatic and more stable. Right next door to that, we have a great example of boron. So boron does not get to choose. It always has to be sp2. However, no electrons. So in this case, we have 4 electrons total, and we have to be anti-aromatic. We don't have a choice. Last but not least, I'll show you the double bond outside example. So this double bond is essentially useless. It does nothing. So this is going to be sp2, donates 0 electrons. So all we have is 2, 4, 6 pi electrons. Therefore, that is aromatic. Whew, that was a mouthful. So I will zoom out. If you guys have any specific questions on any of these rules, please let me know. So yes, if the double bond is outside the ring, they basically do nothing. So I like to just pretend it's not even there, and I put a plus sign here, because it acts exactly the same as a carbocation. sp2. Okay. Questions on any of the other rules specifically? If not, I will leave you guys with that. Okay, so I did mention that molecular orbital theory is not something we're going to go into super detail on tonight. This does take forever. But I did want to mention that aromaticity makes molecular orbital theory a tiny bit different. And I gave you all the information about that in the cheat sheet, so you can reference that. But I do want to mention degenerate orbitals, because I know that's easy to forget. Degenerate orbitals are when we have multiple orbitals on the same energy level. And when they're on the same energy level, you have to fill them up 1, 1, 2, 2. So if we have anti-aromatic compounds, the reason they're so unstable is because they have half-filled energy levels, because there's not enough electrons to fill all of those up. Whereas in a aromatic compound, they're both full, and it's really stable. Sorry, I have the hiccups. It's really annoying. Okay, I will give you a moment. If you have any if you have any questions, let me know. If not, we're going to move on back to the other handout, and we're going to start chapter 15. Okay, doesn't seem like there's any questions, which is a-okay. If you have any, let me know. Chapter 15 is all about electrophilic aromatic substitutions. We spent a lot of time on this chapter, and I did send you like a cute little summary table thing. But if you're not really a visual person and you like things just listed out, this is for you. So a nitration reaction, these are the reagents, this is the electrophile, and the product would be benzene ring with NO2 on it. Sulfonation, these are the reagents, this is the electrophile, and the product has SO3H. Halogenation, these are the reagents, this is the electrophile, and the product looks like so. These three are all pretty much the same. Everything about them is the same. The reaction mechanism is the same. They all need a Lewis acid, things like that. The ones that are a little bit different are Friedel-Crafts, And so the reason, Friedel-Crafts are a little bit different is, one, you always know it's a Friedel-Crafts reaction if it has AlCl3. That's only for Friedel-Crafts. Now, Friedel-Crafts alkylation has a carbocation as the electrophile, so we have to watch out for rearrangements. And the final product will look like so. And the note here is can have polysubstitutions. The Friedel-Crafts acylation is interesting because we have the Acilium Ion. You do have to know that one by name, unfortunately. And the reason this is interesting is because both of these are the Acilium Ion. This one is more stable because O holds charge better. So the oxygen is better at holding a charge than the carbon. That's just something you should know in case he asks you, like, which resonance stable. In case he asks you which resonance structure is more stable, then you know. I'm going to give myself a moment because that was apparently a really hard sentence to get out of my face hole. They're back to last semester when I actually went through and I edited all these mistakes out. I now have no cares. You guys can witness my strokes. Okay, so what we end up adding to the ring is the carbonyl and the R group. Something that's true of both Friedel-Crafts reactions. So I'll do like this. They can not happen with NH2 or a strong deactivator. So if we have a strong deactivator or NH2 on the benzene ring, this will be no reaction. So I'll leave this for a moment because I did write a couple notes on here. Okay. So I have the reaction for you. I don't know that I want to cover every step of the mechanism. I don't think it's that important. So just know starting material, reagent, final product. And, okay, look, I'm not saying that you shouldn't look at the reaction whatsoever. I'm just saying it's not, like, one of the biggest things of the semester, so I'm not going to spend this time on it now. You should, of course, look at it when you're studying. All right. So that is the end of the handout that I posted for you guys, which was mostly the other two chunks. So we haven't done chapter 12, 16, 17, or 18. And there's a reason for that. So I'm going to pull up chapter 12, which is all the way up here on page 9 of this handout. 9 is ridiculous. It's a lot of pages. This was a lot of pages. I feel so bad for you guys. But anywho's. So we're going to do chapter 12. And then for chapter 16 and 17, I figured the most effective way to do it is to make like one big summary table together. So that's what we're going to do. So chapter 12 is oxidation and reduction, and we call those redox reactions. And so I already listed out the reagents and stuff because we spent a lot of time talking about them previously. Just remember, if we have O4 or more, that's going to be a strong oxidizing agent. And so I'll go ahead and highlight that, O4 or more. We also know that B and A comes before B in the alphabet, so that has to be stronger. That doesn't make any sense, but that's how I remember it, so you're welcome. We know that an oxidation reaction is making more bonds to oxygen. A reduction reaction is reducing the number of bonds to an oxygen. So we're going to go through and we're going to like really simply go over all of these reactions. In the handout, I gave you guys a little trickety trick and I drew out tertiary alcohols and I asked you what the product would be. Surprise, it's no reaction. So a tertiary alcohol is not going to be reduced. I'm so sorry. A tertiary alcohol is not going to be oxidized. I'm a mess today. I do apologize. All right, so let's do our oxidation reactions first. If we have a primary alcohol with a strong reagent, we get a carboxylic acid. If we have a primary alcohol plus a weak reagent, we get an aldehyde. So primary plus strong equals carboxylic acid. Primary plus weak equals aldehyde. If we have a secondary alcohol, it does not matter what kind of reagent you have. So whether you have a strong reagent or a weak reagent, we only have one hydrogen to get rid of. So we're always going to make a ketone. Don't let him trick you. Both strong and weak reagents reacted with a secondary alcohol will give you a ketone. So I'll zoom out right quick. That's all there is to oxidation. Reduction, we went over a lot of steps and I showed you all the reduction reactions, but honestly, as far as this exam goes, as you know the summaries, you should be good to go. So that's what we're going to do today. First things first, actually, before I even do that, we're going to talk about group 1 versus group 2. So group 1 is the aldehydes and ketones. Group 2 is the carboxylic acids and esters. And before we go any further, I just realized that those are both ketones. So please put a hydrogen here so you know that one of them is an aldehyde, one of them is a ketone. That's my bad. Okay, back to what I was saying about group 1 and group 2. Group 1 is more reactive, and group 2 is less reactive. So the more reactive group can use either reagent. So we can say either. And before I do it, someone asked a question, which was, are you going to break up the video so it doesn't fall apart like last time? Yes, I am. So each hour is getting its own video just so the recording doesn't like completely flip out. So we are on hour 2 right now. We are on recording 2, and there should be one more. Also, welcome back. Okay, so group 1, more reactive, either reagent. Cool. And we are going to get aldehyde gives us a primary alcohol. Ketone gives us a secondary alcohol. Doesn't matter what reagent it is, you get the same answer. So ketone, secondary, aldehyde, primary. These guys are a little bit different. They're less reactive and they have leaving groups. So the less reactive part means that they have to react with the stronger reagent, which is LiAlH4. LiAlH4. And we are going to replace the leaving group. Wow, that was swag. We're going to replace the leaving groups with a hydrogen. So we end up with an intermediate that looks like this, and a final product that is a lovely primary alcohol. And the ester has the same exact answer. So we get a aldehyde intermediate, and we get a primary alcohol as our final product. The hiccups have turned into coughs, so that's fun. All right, I know that was super fast. I know, I'm so sorry. But I hope it was okay. So Diba, you probably weren't tested on this. He probably will bring it up for the final. So Diba is a strong reagent that only works with carboxylic acids and esters. So it only works with group 2. And it only goes up to the aldehyde step. So we don't get a full reduction. We stop at the aldehyde. So just remember that. Okay. Any questions, comments, concerns? That's pretty much all I have on here for chapter 12. We are going to talk about the Grignard reaction, but you know what? Yeah, let's just talk about the Grignard reaction right now. I was going to put it in the next video, but there's no point. So, Grignard reaction. Hold on. Someone had a question. So someone asked, so does it matter if the OH is primary or anything? So are you talking about oxidation or reduction? Either way, it does matter, absolutely. So what I want you guys to do is go through all of these and kind of write out your own summary in a way that makes sense to you. But it's something along the lines of primary alcohol plus strong equals carboxylic. Primary alcohol plus weak equals aldehyde. Secondary alcohol plus strong equals ketone. Secondary alcohol plus weak equals ketone. For reduction reactions, aldehyde plus either primary, ketone plus either secondary. Carboxylic acid plus LiAlH4 equals primary. Carboxylic plus Diba would only be an aldehyde. It wouldn't go to an alcohol. And same thing for the ester. Always makes a primary. Okay, cool. The last thing I will mention for this, I really stressed it for the exam number 2. Remember, the reducing agent is NABH4, LiAlH4, Diba, but the reducing species is H-. So that is the thing that's doing the actual reducing. I'm shedding. Okay. Anywho's, that was a lot. Woohoo! We got through it. Yay. Okay. So the Grignard reaction is kind of interesting. Or the Grignard or whatever. This is truly one of the most annoying names in this whole semester. But the Grignard reaction starts off with making the Grignard reagent. So you should also know that the Grignard reagent is also called the ylide. And this happens with some kind of alkyl halide, right? And we react the alkyl halide with Mg and ether. And Mg is jealous of carbon and the halogens relationship. So just to make it more personal, I'm going to change this to a bromine. And I'm going to set the stage for you, right? We're going to jump right into like a soap opera. So bromine and carbon fell in love. They've been in love for a long time. Happily married. Magnesium is a little bitch. Sorry. It's going to come in and it wants to seal bromine all for itself. And in order to steal it all for itself, it slips in here and it breaks up their marriage. So we get our carbon, and our carbon just lost the love of its life. It's so sad. You can see it's a frowny face. It's negative. Very negative. It's not happy. In addition, bromine is sitting there. It's kind of doing its own thing. And magnesium is really happy about it. It's like, haha, I got the girl. Sucks to be you. You know, just real homewrecker, right? And so now they're happy together. We don't care about them anymore because they broke carbon's heart and we stand carbon. So they can go off in their own cloud of betrayal. Bam. So since we're Team Carbon, right, we're going to call Team Carbon Grignard. That is the Grignard. And someone pointed something really great out. I am just on a different planet today. The Illid is in fact not for the Grignard reaction. It is for the Wittig reaction. So please ignore that. It's just called the Grignard reagent. I'm sorry I had a mini stroke. Thank you for pointing that out. We're going to pretend that never happened. I was going to say ignore everything I say, but that would contradict the fact that you came here to learn from me, so I'm not going to say that. Instead, let's tune back in and see what's going on with Mr. Grignard here. So Mr. Grignard is so desperate for love. So desperate. He's going to go and try to bond with anything around it, right? So Mr. Grignard can be a really strong base, or it could be a very strong nucleophile. It really doesn't care. It's going to snatch whatever it can, right? So we have to be careful, right? We want to set Mr. Grignard up with our friend, right? So we have a friend. Her name is Senora Ketone, or any kind of carbonyl, really. So we try to set him up with Miss Ketone, and let's see how that goes. And Mr. Grignard is so sad he turned blue. He's negative and he's blue. Okay, so Mr. Grignard is going to go ahead and he's so desperate for love, he's going to make a bond right here and kick up these electrons, right? And we end up, they very quickly fall in love. And they have this brand new wonderful bond right here. And we add this carbon chain to the carbonyl carbon. Of course, we don't want to leave oxygen feeling negative, right? So what we're going to do is use some H2O in solution to protonate, and we get a happy family that we like to call a tertiary alcohol. Let's say, though, alternate ending, let's say instead of hooking him up with our friend Miss Ketone, we instead hooked him up with our friend Miss Carboxylic Acid, right? So we know that Mr. Grignard would have a really good time with the carbon right here, right? But he's not going to take the time to get to know that carbon, right? It's hard to go all the way in here, get to that carbon, do that reaction and everything. Why would he do that when there's a little hydrogen right there, nice and acidic, waiting for a base to pick it up? He's just going to go for the base, right? He's not going to go for that carbon. So anytime we have an acidic hydrogen, that Grignard is just going to snatch that right up, and we get no reaction because this guy is going to act like a base. Yeah, it can't happen with an acidic hydrogen. Wait, oh my goodness. I don't know what accent I just developed. It cannot happen with an acidic hydrogen. There is an example that we're going to cover later that's like a multi-step reaction, but we'll talk about that when we get to it. All right. Cool. And scene. Ta-da! That was our lovely Grignard show. It will be dropping on Netflix next week. I'm just going to keep talking if no one asks questions. If we don't have any questions, it is the end of hour 2, so I do want to stop the recording and restart it. Before I do that, any questions, comments, concerns, anything of the sort? Okay. So, I'm going to stop the recording now.